Okay, my name is Yizhi Xiang, and I'm an assistant professor at Chemical Engineering Department at Mississippi State University. I'm doing research and teaching undergraduate classes. Now let's go to the lab. Okay, so I finished my PhD back to 2010 in China, and then after my PhD I moved to Brussels at Belgium for postdoctoral, and then after about 3 years in Brussels, then I moved with my supervisor to Washington State University, and I helped him set the lab and doing the research there. And then since 2016 I moved to California and working in the company called Nice America Research, and then after about a year, then I moved to Mississippi State University. And the reason I moved here from industry because I'm doing research, I like it, and I like to do independent research and to do whatever idea I have. That's why I moved to university. Okay, so our department is one of the major parts of course teaching, right? We're teaching undergraduate students, and another major part is doing research. So we have different faculty here doing different kind of research, and we have a lot of collaboration with each other. Like I'm doing catalysis, other people working on materials and working on batteries, and there's also faculty working on the modeling, advanced modeling for the understanding different processes, what is the underlying reaction mechanisms. So we're doing different collaboration with each other among the faculties. I liked research, as I said, and I really enjoyed by having new ideas which are related to my research, and I really enjoyed when we have the experimental process which verify my ideas. And I also like to summarize results and like to analyze the results, and of course I also like to writing paper for publication which can share our results to the whole community. My main interest or overall interest is catalysis. So in the whole chemical engineering process, we're using up to 90% of the process using catalyst. And the catalyst can accelerate the chemical reaction process, can enhance the selectivity of the chemical reaction. So that's why in the chemical engineering process, we're using a lot on the catalyst. So my main research is on the catalyst design. We try to design useful catalysts or very efficiency catalysts to transform these chemical reactions. My current work is mainly on the light alkanes conversion. So light alkanes means like natural gas. Like natural gas, we have the methane or ethane, these light alkanes. And the natural gas can be, of course, being burned for cooking, but what I do, I want to convert this natural gas to more useful chemicals or fuels. So I want to convert the natural gas, for example, to gasoline, which can replace the petroleum as a fuels. I can also convert the natural gas to the aromatic liquid products. That's also a very important feedstock for different chemical products. And then we try to develop catalysts to efficiently convert this process, because normally it is not easy to convert light alkane because they are very stable. Because for example, methane CH4, this hydrogen carbon bond is very stable, and normally without catalyst, it can never do the transformation. So what we do, we try to develop a catalyst to breaking the bond, and then in the meantime forming the new bonds, and then create our products. I'm looking more into the sustainable energy and the chemicals. That's still also part related to my current research. And most of the chemical engineering process right now is still very highly carbon and energy intensive. For example, the ammonia synthesis is very high temperature, very high pressure, and it produces a lot of carbon, CO2, which is greenhouse gas. And what I'm thinking right now, which also is working by the whole other peers, we are thinking about using renewable electricity to drive the plasma and doing together with the catalyst, then we can realize the reaction at room temperature and which is less carbon intensive. We have two major achievements, I think. And one is we developed a new chemical reaction. That's a reaction previously has not been studied. So we co-processing lead alkane with ammonia and using a bifunctional catalyst, and then we produce in one step, which called acetonitrile. It's very important solvent for the battery, for the chemical engineering process. So we produce this in one step from a cheaper material. And in industry right now, they come from more complicated process. So we reduce the price for the production. And another part is traditional chemical process, but it's very expensive catalyst which is used. They're using some noble metal platinum on the zeolite, and they're using higher loading. And we try to reduce the loading, for example, to 100 ppm level. So in this way, we reduce the usage of the noble metal, then we reduce the cost of the catalyst, of course. For what I'm doing right now, related to the lead alkane conversion, the most challenging part is to find the stable catalyst. So the catalyst, like what everything else, has lifetime. And the lead alkane conversion, because it's very stable, then we have to use high temperature. And at high temperature, then the lifetime of the catalyst will decrease. And for example, at high temperature, the catalyst will cooking, and which means the carbon will deposit on the catalyst. And then our catalyst will be covered by carbon, then it will lose the activity. So that's the most challenging part, to how minimize the coke depositions. That's the most challenging part.